Hello, my name is Matthew Rondinella, and I'm presenting the fourth physics lab on oscillations. For the background concepts of this lab, an important one is the momentum principle. Since changes in momentum are proportional to net forces, we can determine that the nonlinear motion of the object is caused by net forces of the spring and gravity as seen in the video motion analysis. Additionally, the energy principle is important because there are many types of energy in this system, but ideally, the sum of these energies should always maintain its current value. Work represents conversions of energy. So for example, when potential energy forms are translated to movement in kinetic energy, that would be represented as work on an object. In order to analyze the beginning conditions in the video, the spring is stretched and held to the left a little bit. And the way that this is useful information is that we know the spring force is always on the perpendicular axis or towards the anchor point of the spring. And now if it's stretched, this is relatively upwards, or if it's compressed, this is downwards as seen in these two diagrams. Gravity is a constant downward force, and it's the gravitational potential energy that plays a role in the system. So for the tracker data and recording, I marked each frame of the video and calibrated using the distance given in the edX tutorial video, and I gathered the data points in a table format. Now, with this information, there are important values we can derive to plug into our glow script to create an accurate computational model. So since the mass was given as 0.402 kilograms, and we know that the initial spring length, or its current stretched length, was 0.7 meters, we can make important calculations, as you can see, based off the period of the spring itself. But first, we need to establish a delta t, which is 1 over 210 seconds, because that is an integer multiple of the time between frames of the video. Now, returning to the period statement, the period of oscillation of a spring is equal to 2 pi times the square root of mass over the spring constant. So, in order to determine this unknown spring constant, which we need to plug into our glow script code, we can simply look at a graph of our positional data we got from tracker. So as you can see, the first trough occurred at roughly 0.665 seconds, and the last one at 8.357 seconds, or 5 periods later. So dividing this time interval by 5 gives us a period length of 1.538 seconds. Continuing, we solve the period formula using this information, and we get the unknown spring constant of 6.706 newtons per meter. Additionally, the rest length, we can determine that when the spring is initially at rest, the upwards force of the stretched spring is equal to the downwards gravitational force. So making an equation here, we can determine that S, or the stretch amount, is equal to the stretch length minus rest length. And we know that numerically, the stretch length from this equation is 0.587 meters, or rest length is 0.113. So now with this valuable information, I can plug it into GlowScript to create a model. So plugging in the mass and the initial positional data as recorded from tracker, and the delta t initializes the spring system. Using the values of the spring constant and rest length that we've determined, we are able to also set conditions. For the computational loop, this simply L, or the stretched length, would simply be the spring position, or the ball position minus the spring position. So the distance between the mass and the spring itself is the spring length. L hat is the vector divided by its magnitude, and the stretch length is the magnitude of this spring's length minus the rest length. For the energies, I use the formula for kinetic energy, 1/2 mv squared, potential energy, mgh, and spring energy, 1/2 ksx squared. And the total energy is the sum. Going through the calculation loop, the force of the spring is negative kx, ksx, and times L hat for direction. The net force is the addition of these two forces, and using the velocity update formula and position update formula, we can continue gathering the data that GlowScript models. So for the energy changes, it's simply final minus initial for all 4 types, and we get these graphical results. So for the positional data, you can see that it does mostly resemble the same. However, it seems to be dampened for the real world data in the sense that the oscillations are not as large. And also for energy in the GlowScript model, you can see total energy is conserved, while there's a trade-off between both of the potential energies and kinetic energy, where they are both at 0, the kinetic energy is at a maximum. So overall, the energy has been conserved from the system as evidenced by this orange line. And another important comparison is the period of oscillation. The tracker value is 1.538 seconds, but using the GlowScript readings, we can determine through a similar method of comparing 5 periods that the time interval is actually slightly longer and the period takes longer as well. Now, this is most likely due to the existence of air resistance in a real world trial because energy is lost from the system to the surroundings as heat in the form of friction. And because of this additional force that was unaccounted for in glow script, but in reality, this would slow down the mass and make the oscillations appear shorter. So overall, the glow script model showed that energy was conserved, but in reality, some of that energy was lost to the system. Energy was lost from the system to the surroundings as heat.